Hello everyone, welcome back to Physics 425. So what we were thinking about in the last set of videos was the grand partition function. In fact, the grand canonical ensemble from which we could calculate the grand partition function. And so I've written that result down here. It's a sum over all of the quantum states of this exponential of minus the energy of the state minus mu times Ni, where Ni is the number of particles in state I divided by kBt. And so remember, in the grand canonical ensemble, the number of particles in a state or in a system can be variable. The goal for today is to see if we could write down the result, a general result for the grand partition function for a generic system of bosons. And then we want to use that to calculate things like the pressure and entropy and heat capacity of the boson system in both the high temperature and the low temperature limits. Okay, and so you may recall that we use this grand partition function to calculate we use this expression to calculate the grand partition function for a single energy level that could be occupied by any number of identical bosons. And so the result was for a single energy level that can be occupied by any number of bosons we had this result where, let me write it with a subscript k vector, and so what this is going to represent is the grand partition function for a single quantum state or a single energy level. And in fact, we use this to derive the Bose-Einstein distribution function. And remember, what it ended up being is we could write this as a geometric sum that we could write down the solution for, and it looked like this result. And so epsilon of k is the energy level, and we minus the chemical potential, and I'm going to run out of room here. Let me try this again. Let's see if I can fit this in a single line. So 1 minus e to the minus epsilon k minus mu over kBt and all to the minus 1. Okay, so what I want to do is I want to generalize this result, and I want to think about a system of not just a single energy level, but a complete system where we could have bosons occupying a bunch of different energy levels. So if we consider the grand canonical ensemble of the entire system, that is many energy levels of different k vectors, I claim that this complete grand partition function can be constructed by taking the product of the grand partition functions for the individual single levels. And so that's going to be the product of this expression that we had, 1 minus e to the minus epsilon of k minus mu over kBt all to the minus 1. So that's the claim. I think what we can do is we can demonstrate that this works for a small system. And so let's, for example, consider only two energy levels, each with 0, 1, or 2 particles. Okay, and so we could imagine we have the following. So there's energy level with energy epsilon 1 and one with energy epsilon 2. And so one possibility is that both of those levels are completely unoccupied. And then another possibility is we have one particle in the bottom level, or we have two particles in the bottom level. And then we could say, well, maybe the bottom level, epsilon 1, is empty and there's one particle in the second level. And we can just go through and we could write down all of the different possibilities. And so there could be none in the bottom state and 2 in the upper state. So we'll do all the cases with 2 particles in the upper state. And so that's all of the possibilities. And so if we were to write down then for this system the net grand partition function, we would just have to sum all of the different exponential terms. And so first one would be 0 particles and 0 energy, and so we'd get e to the 0, which is 1. And then the second term is going to be e to the minus. The energy is epsilon 1 with 1 particle and 1, n equals 1 over kBt. And then the third term would be e to the minus. Let's see, there's going to be 2 epsilon 1 minus 2 mu over kBt. And so these first 3 terms correspond to these first 3 cases. Okay, and then we go to the next set of 3 is we've got 1 particle in the upper energy level. And then next we have 1 in each of the levels. So we'd get an epsilon 1 plus an epsilon 2, and then we have 2 particles over kBt. And then let's see, the next one would be plus e to the minus, and then we have 1 particle in the second state. Let's do it the other way. We have 2 particles in the bottom state and 1 in the upper state, and so we'd get 3 mu over kBt. And then I made a mistake, this should be a minus sign. Okay, and so these next 3 terms correspond to the next set of 3 states of our system. And so finally we've got 3 more, so plus e to the minus 2 particles in the upper state, 2 epsilon 2 minus 2 mu over kBt plus e to the minus epsilon 1 plus 2 epsilon 2 minus 3 mu over kBt. And then finally 2 particles in each state. 2 epsilon 1 plus 2 epsilon 2 minus 4 mu over kBt. Okay, and so these last 3 terms correspond to the last 3 states of our system. So what we claimed was that what we could do is we could write down the grand partition function for a single state, say the epsilon 1 state, and then multiply it by the grand partition function for the single state epsilon 2, and that product should result in the net. And so let's see what would happen if we tried that. So let's compare that to, for the first epsilon 1 energy state, we could have 0 or 1 or 2 particles. 2 epsilon 1 minus 2 mu over kBt. And then we would have to multiply that by 1 plus e to the minus epsilon 2 minus mu over kBt plus e to the minus 2 epsilon 2 minus 2 mu over kBt. And so this would be 0, 1, and 2 particles in the epsilon 2 state. Okay, and so if we look at the, let's see, the green terms. So let's get our green marker. So the first is 1, so we'd get 1 times 1 would give us the 1. And then it would be 1 particle in the epsilon 1 state, and so we would have this product. And then we have 2 particles in the epsilon 1 state, and so that would be that product. And so that gives us the 3 green terms, and the red terms is going to always have 1 particle in the epsilon 2 state. And so the first case is going to be, let's see, 1 times this gives us the first red term. And then we have 1 particle in each state, and that would give us the second red term. And then we'd have 2 particles in the epsilon 1 state and 1 in the epsilon 2 state. And so that product would give us the third term in the red set. And then finally we have the blue set, and so it's going to be first 2 particles in, we're going to have 2 particles in the, let's see, right, okay, 2 particles in the epsilon 2 state, and then 2 particles in the epsilon 2 state and 1 particle in the epsilon 1 state. And so we would have this, and then 2 and 2. And so if we did out all those multiplications, we would reproduce the 3 terms that we wrote down originally. And so what we've shown is that we can write epsilon net is equal to the grand partition function for all of the particles in the state with energy epsilon 1 times the grand partition function for all the possibilities of particles in the state with energy epsilon 2. Okay, so in general then, if you had many, many k-states, it's still true that the total grand partition function can be written as the product of the grand partition function for any of all the individual states. Okay. So what we can do then is we could calculate the grand potential. The grand potential is useful because we can take derivatives of the grand potential to calculate thermodynamic quantities like pressure and entropy and so on. So therefore, the grand potential for our many-level system is the grand potential is, remember, it's minus kBt times the ln of the grand partition function. Okay, and so that's going to be minus kBt times the ln of this product. So what's nice about this is that we have a product. Well, we have the ln of a product, and then you can write the ln of a product as a sum of lns. And so this is equivalent to minus kbt times the sum of over vector k, and it's the ln of 1 minus e to the minus epsilon k minus mu over kbt, and that's all to the minus 1 power. So now we have the ln of something to some power, and so we could take that power and move it out front. Our power is minus 1, and so it just kills the minus sign, and so we end up with a plus kbt times the ln of k. The sum over k of the ln of 1 minus e to the minus epsilon k minus mu over kbt. And I forgot my t over here, so we'll put that back. All right, and so that in general is the grand potential for a many-level system of identical bosons. So if you recall back to maybe a few weeks ago, we were able to rewrite these sums over k vectors as integrals. And let me remind you of how we did that. So it involved the density of states, and in general what we were able to do is to say if we have a sum over a k vector, and that sum acts on something that depends only on the magnitude of k, and so this f of k is going to be any function of the magnitude of the k vector. And, look at our grand potential. It involves a sum over vector k, but what we have inside the sum is the ln of some stuff, and so this depends only on the magnitude of k, right? So that's the argument inside the sum doesn't have any vector dependence on k, it's just the magnitude of k. So in this case, we were able to convert this sum into an integral over the magnitude of k. We just had to have a prefactor, which was volume over 2 pi squared, and then we got k squared times that function and integrated over the magnitude of k. And so I want to apply that to our grand potential, and when we do that, we get that the grand potential of our boson system is going to be v over 2 pi squared. We're going to have still our kbt out front, and instead of a sum, we're going to have an integral 0 to infinity, and we pick up a k squared, and then we have ln of 1 minus e to the minus epsilon k minus mu over kbt, and we integrate with respect to the magnitude of the k vector. And so this is our grand potential for our boson system. So this is a general expression for the grand potential of a system of bosons. And so this is valid for any temperature T, and it's valid for any form of epsilon k. We're ultimately going to try to evaluate this for a system of non-interacting bosons, and so we'll write the energy of the k states as h bar squared k squared over 2m. But in principle, if you had some kind of different energy dependence on k, you could go back to this general expression and plug that in and then evaluate it. Okay, so what I want to do is I want to take a look at this expression, and I want to see if we can come up with some limiting behaviors in the low temperature and high temperature case limits, I guess. And so let's consider first the low temperature limit. So one thing that we know is that this, remember, eta was defined as mu over kBt, and so we have mu over kBt in our expression here. And so we thought about this ratio in the limit that t goes to 0. So we know that eta goes to 0 as t goes to 0. So if we had some kind of log scale, log t versus eta, and if this is 0, what we found is that as we approach 0 temperature, this eta approached 0, and then as temperature increased, it was a negative value. Okay, so therefore, in the low T limit, what we could do is we could just say, well, let's suppose we're at a low enough temperature that the mu over kBt in the exponential just becomes 0. And so in that case, we just have the energy epsilon of k over kBt. So that's the only change we're going to make. So in the low temperature limit, our grand potential expression looks similar. We're just going to drop the chemical potential, mu, in the exponential. So this is our low temperature limit. I'm going to leave a little space under here, and I'm just going to emphasize that this is only valid for bosons for which mu over kBt goes to 0 as t goes to 0. And let me call this equation 1, and we'll probably refer to it a little bit later. Okay, so let's now look at the high temperature limit. So for a gas of particles, and in this case, we're going to allow our gas to be fermions or bosons. In the dilute and high temperature limit, we saw that eta, which is mu over kBt, was equal to ln of n over nq, where nq, remember, was this quantum density. And we found that this is large and negative. In fact, I mean, we just plotted this thing. So in the high temperature limit, we have a large negative number for eta. So this is the high T limit. And this NQ, this quantum density, was given by m kBt. M is the mass of the particles over 2 pi h bar squared to the 3/2 power, and little n is the number density. You know, we started by thinking about only a system of bosons, but now what we're going to do is we're going to apply the high temperature limit results to fermions and bosons. The reason we can do that is because we're thinking now of high temperatures and a dilute gas. And so remember, in a dilute gas, the chances that any two particles would want to or try to occupy the same energy level is very small. So that probability is really small. And so in that case, the Pauli exclusion principle becomes irrelevant, and it doesn't matter if we're talking about fermions or bosons. Okay. So, let's see, in this case, if we were thinking about the Bose-Einstein distribution, for example, the exact expression for the Bose-Einstein distribution is like so. And in this high temperature dilute limit, mu over kBt is a large negative number, so we have e to the minus mu over kBt. Sorry, I forgot my divide by. This is kBt. And so e to the minus mu over kBt is a large positive number, and we can forget the minus 1. In fact, if this was a Fermi-Dirac distribution, we'd have a plus 1, but we would still just forget about the plus 1 in that case. And so whether we're talking about fermions or bosons, then the distribution function in this limit becomes e to the minus epsilon k minus mu over kBt. Okay, and so therefore this e to the epsilon k minus mu over kBt is large because the minus mu over kBt is large and positive, or 1 is much greater than if we were to take the inverse of this expression. We'd have e to the minus epsilon of k minus mu over kBt. And so when we take the inverse, then we have 1 over a large number or a very small number. Okay, and so this is now small. Okay, and so what we have inside our expression for the grand potential is a ln of 1 minus e to the minus epsilon k minus mu over kBt. And so we've just argued that this is small. The exponential is small. Well, let's recall that if you have ln of 1 plus x, that's approximately equal to x for x being a small number. Okay, and so we have 1 minus a small number, and so this is going to be approximately equal to just minus the small number. Right, so I could put a plus or minus here, and then I could have put a plus minus x over there. Okay, good. Okay, and so this is equal to minus e to the minus epsilon k over kBt times e to the eta, where eta is mu over kBt. And so therefore, what we have in our high temperature, and let's emphasize dilute limit, the grand potential is approximately, so let's just go back to the general case here. Where is it? So we're going to replace this ln inside the integral with this approximation of minus e to the epsilon k over kBt e to the eta. So what we're going to pick up is an overall minus sign. We're still going to have the v over 2 pi squared. We're still going to have the kBt factor. The integral is over k, but eta is chemical potential over kBt. It has no k dependence, and so we could take out the e to the eta outside the integral. Then we have the integral 0 to infinity. There was a k squared, and this is where the ln was. It was multiplying the k squared, but now we've just replaced that with e to the minus epsilon k over kBt dk. I'm going to call this equation 2, and we'll put a red box around it. And let me emphasize that this now is valid for both bosons and fermions. And so now what we have is approximate expressions for the grand potential, both in the high temperature and low temperature limits. In the low temperature limit, our expression is valid only for bosons, and in the high temperature limit, it's valid for bosons and fermions. Why is this useful? Let's just recall something that we've done before. The grand potential we were able to write as internal energy minus Ts minus mu n. So that if we take a differential of the grand potential, that's going to be du minus T ds minus S dt minus mu dn minus n d mu. But du is dq, which is TDS, and then it's minus pdv for the mechanical work, and then plus mu dn for the chemical work, and then we still have our minus TDS minus S dt minus mu dn minus n d mu. And what was nice about this is that there was lots of cancellations. Mu dn and mu dn, and TDS and TDS. Okay, and so that means the differential of our grand potential has remaining P dV with a minus sign minus S dt minus N d mu. And so, for example, if we hold T and chemical potential mu constant, we could write P as minus d phi g dV at constant T and mu. If, on the other hand, we hold V and mu constant, we could write the entropy as minus d phi g dt at constant V and mu. And then, of course, the other one is chemical potential is minus d phi g it's not chemical potential, it's particle number. N is minus d phi g d mu at constant V and T. Okay, let's just emphasize something here. In the low temperature limit, where is it? We set mu to be 0, and so there is no mu dependence in this phi g, and so this last expression, this derivative with respect to mu, is we can't use it in the low t limit because we set mu over kBt to 0. So just to emphasize that. But what we can do is the entropy can be related to CV, the heat capacity, and that relationship is T ds dt. So once we've calculated S, we can then go on to calculate heat capacity. So one thing you can do, which is quite nice, is for a gas of free or non-interacting bosons, what we could do is we could set our epsilon k to be just kinetic energy, h bar squared k squared over 2m, and we can use 2 to find that in the high T limit, P, you should be able to guess what it is. It should just be the ideal gas law. PV is NKT. And the entropy should be what we expect for a dilute gas. And it's this Secker tetrode equation. And the heat capacity should be a constant. It depends only on the number of particles, 3/2 n kb. And so I think I'm going to leave for homework. But what's really nice about this result is that we started with quantum theory, right? We started with a grand partition function, which was a sum over quantum mechanical states, and we were able to write down the result for a general system of bosons. And when we consider the high temperature limit and we consider non-interacting bosons, then we recover all of these classical results that we've known since, our thermodynamics class. So we've recovered the classical results starting from a quantum theory of identical particles. Okay, and then the other thing that you could do is you could do the low temperature limit. So for a gas of free bosons, we can use equation 1 to find in the low temperature limit what you should find is that pressure is proportional to T to the 5/2. And so that's different than the classical result where pressure was proportional to just T, and entropy is proportional to T to the 3/2. Again, that's different than what we had for the classical gas. And for the classical gas, we had CV was independent of temperature. It was a constant. And so in the low temperature case, that again is different. And so this will also leave for homework. Okay, good. So I think that's a good place to stop, and we'll pick it up from here next time. All right, thanks very much.